So how we define the term energy? Energy refers to ability to do work. And you will find a very common term for all these definitions of different forms of energy. Ability to work, ability to work. Because how we define the term energy, energy refers to ability to do work. So different forms are there. Some of them you will learn in detail about the calculation. For the others, you just have to know the names. When we say about the kinetic energy, how we define the term kinetic energy, it's ability to do work due to the movement of an object. Like when we are able to move an object possess some speed, we call that as a kinetic energy. Gravitational potential energy. The gravitational potential energy is ability to do work due to the position in the gravitational field. If we change the height, if we change the position, the height actually in the gravitational field, we call that work done as a gravitational potential energy. Elastic potential means when we apply force and we deform the object, like compressing or stretching the objects, what we call elastic potential energy. Sound energy is ability to do work for the particles which are having kinetic and potential, like vibration of the particles, if we call that as a sound energy. Internal energy, how we define the term internal energy, it's actually a sum of kinetic and potential energy of the particles. Electrical potential, it is a work done to move the charge in electric field, we call electrical potential. There is a difference between electrical energy and electrical potential. Like there is an electric field, but about this you will learn in A2. This also you will learn in A2. Internal also in A2. Sound energy also in A2. This is in AS, the three. Elastic potential, kinetic and gravitational, these three are in AS. Rest all of them are in A2. About the chemical, you will not learn anything in detail about the chemical energy. So we have a gravitational potential energy, which is mgh, and we have a kinetic energy, which is half mv square. And elastic strain energy, about the elastic strain energy, that will be the topic, like our next topic, which is about the properties of the material. So whenever object changes a position, there is always like a law of conservation of energy, that energy cannot be created nor be destroyed, but it changes from one form to another. Say, if we assume there is no loss of energy and the object is there of mass m, is dropped from a height h. So which form of energy the object is having at a maximum height, it will have a gravitational potential energy or mgh. And when the object is moving, it's kinetic, because the speed will change. As the speed will change, the kinetic energy will increase. So which form of it will have kinetic energy all around, but which form of at the base, the kinetic energy, if I say the speed at which it's about to hit the ground is v, so the kinetic energy will be half mv square. So what is the energy change here? All the gravitational potential at the maximum height transformed into kinetic energy just before it hits. So we can say the change in the GPE, the change in the gravitational potential energy, is equals to gain in kinetic energy. So potential energy is mgh and the kinetic energy is half mv square. So when we simplify this formula, m will cancel with m. So we have the gh is equals to half v square. So what it shows that if there is no loss of energy and there is no air resistance to oppose the motion, then the speed at which the object hits the ground, it does not depend on the mass of an object, because you can see the mass is not the factor here. So even if I drop a 2 kilogram object, I drop a 5 kilogram object, I drop a 50 kilogram object, all the objects will hit the ground with the same speed with no air resistance, and the acceleration due to gravity is constant. So the change in the gravitational potential equals to gain in kinetic. So half mv square will be equals to gh. So GH is equals to half V square. So mass is not the factor. So this formula also confirms that whenever falling objects without air resistance, if there is no loss of energy, then the gravitational potential energy equals to kinetic, or GH is equals to half V square. This is the case when there is no loss of energy. And same thing when object is launched vertically upward with a velocity V and which reach the maximum height H. So in that case also I can use a formula, because in this case the kinetic energy transformed into gravitational potential energy. So kinetic is half mv square and gravitational is mgh. So when we simplify, it will be half v square is gh. So the same formula we get, but what is our assumption? If there is no air resistance, then this is valid. But what if we have the air resistance? In that case, the formula will not be same. So if there is an air resistance opposing the motion, so in that case, for example, there's an object of mass m, and it is dropped from a certain height h. So on object of mass m, it is dropped from certain height h, and there is a air present. And what air will do? Air will oppose the motion. The air resistance will always oppose the motion, so it will act opposite to the direction as the object is released. So it will have a gravitational potential energy, or GPE here, and it will have a kinetic energy here. But because as it is moving, the air resistance opposes the motion, so it will lose some of the energy, or some of the work is done against the air resistance, or work done by the air to oppose the motion. So what will the equation we write in this case? So we'll write, in this case, the GPE, the gravitational potential energy, is equals to sum of the work done against the air resistance plus the kinetic energy. So gravitational potential energy is mgh. Work done against the friction, so it will be F into D, like the frictional force, and for what distance? This D. If the air resistance was acting through the whole motion, then it will be F into H. But for a certain part of a motion, if the air resistance is acting, like if I say the air resistance was acting effectively in this region, so that distance I will say that distance is D. And the force of the air resistance is F. So work done by the air resistance, which will be F into D, plus the kinetic energy will be half mv square. So we'll have this formula if there is an air resistance that is opposing the motion. Is it clear, this formula? Anyone having a doubt or a question till this point? Any question or doubt? Okay. Same way, on inclined surface, and if I change the motion, like example, this was the falling object. The object is falling through from the height h. But what if the object is launched vertically upward? So the initial energy will be the kinetic, and it will have a gravitational potential at the top, and there will be some work done against the friction or the resistive force. So what will the equation for us now? So initially is a kinetic. The kinetic energy, some of the work is done against the resistive force, plus the remaining energy will be gravitational potential energy, GPE. And we will write according or solve accordingly. This is when the object is going up, and this one is when object is moving down. On the inclined surface, when object is moving on the inclined surface and there's a friction, so here's an object on the inclined surface and it experiences a force F to move on the inclined surface and it reaches the top, or it reach a height h here. So an object experience, like we push the object, this is the point where we push the object and we provide, like it has a speed v is there. So which form of energy is given to the object will have a kinetic energy. When the object is moving on this inclined surface, the inclined surface is having friction. The friction of the inclined surface, F is there, and the distance which the object moves is d. And it reach the height, the change in the center of the mass. If I'm taking a distance from center to center, so the center of mass, so it was here. So I will take the height as a distance from the center of mass from starting point to the final point. So when we push the object, it has a kinetic energy. But the friction try to oppose the motion and the object cover a distance d. So the friction did some work, like the object did some work done, or work done by the friction to oppose the motion. And at the top, it will have a gravitational potential energy. So when we write the conservation of energy here, like the equation, so we'll write the object is having a kinetic energy at the base. That kinetic energy, some of it converting to the work done or lost because of the friction, work done against the resistive force, plus the gravitational potential energy. The kinetic energy is half mv square. The work done against the resistive force, so F is a resistive force, and the distance which the resistive force is acting, that is d. So I'll write F into d plus the potential energy, which will be mg h, the change in the height. So this will be the formula which we'll use on the inclined surface. Is it clear? The concept of the work done on inclined surface, if there is a frictional force acting on the object to oppose the motion. Okay. So this is about the gravitational potential energy. And the derivation we already did. Next is the efficiency. But before the explanation of efficiency, first we will start with the power. How we define the term power? So the term power is rate of work done or energy transfer. Rate at which the energy transfer or rate of doing a work, that is called power. Whenever in physics, whenever we use the term rate, what it refers to the time. Anything which is related to a time, rate of work done. So it means the power is equals to work divided by time. What about the unit of the power? The unit of the work is joules or Newton meter, and unit of time is seconds, so joules per second, and joules per second is also known as watt, denoted by W. There's also another formula for the power which we can derive. As we know, the power equals work divided by time, and work is force into distance. So force into distance divided by time. And what about the distance divided by time? When the distance or displacement over time, actually, the displacement over time is velocity. So I can say the power is also a product of force into velocity. But what condition you will use this formula. The power is a product of force and velocity, because see, whenever the force is acting on the object should accelerate, the object should change the speed. So velocity will continuously change. But when you use the formula that the power is a product of force and velocity, this force is not the resultant force. This is a force which we require to maintain a constant speed. So this force is not the resultant force. This force is the force which we require to maintain a constant speed. And this V is the constant velocity. Like the best example, say a car. Say there's a car which is experiencing a friction of 100 newtons, and it is moving at a speed of 3 meters per second. The question is how much energy is needed, or how much force, how much power, or what power the engine should generate to maintain this constant speed. So if I want to calculate the power, power is also a product of force and velocity. What is this force? This force is the force required to maintain a constant speed. So if there's a resistive force of 100 Newton backward, how much force I need to maintain a constant speed? If I want to maintain a constant speed of 3, how much force I need? If there's a resistive force of 100, so I need the force of the engine should be 100 Newton. So that is 100 Newton multiplied by the constant speed, which is 3. So we'll get 300 watts or 300 joules per second. So means engine must produce 300 joules every second to maintain a constant speed. So power is a product of force and velocity as well. But remember this formula, when we use a force, it's not the resultant force. It is actually a force which we need to maintain a constant speed. And V is the constant speed which we want to maintain. Is it clear? This concept of the power and the application of this formula, force into velocity? Same way on the, say, a person uses stairs and he reached the top floor. Another person used a ladder and reached the same level. Both are having the same weights. Like example, the weight of the person A is 70 kilogram and the weight of a person B is also 70 kilogram. They reach the first floor, one by using a stair, another one by using a ladder. The person who uses the stairs, he took 20 seconds to reach the top. A person who uses a ladder, he took 10 seconds to reach the top. If I want to compare the work of A and B, what I can say? A did more work than B, B did more work than A, or they did the same work done. If I want to compare the work by A and B, what I can say? They have the same weights, they follow the different routes, but they reach the same level. So what I can say, I can say the work done will be same, because work done does not depend on the route or the path it is followed. But when I'm comparing the power, if I want to compare the power, so power is work divided by time. They have the same work done, but they took different time the one which take the shortest time means he generate or develop more power. So which one generate more power? B develop more power because the time is short. A uses less power because he take longer time to do the same work done. So the two objects may have the same work but different powers depending on the time. If they took the same time and they did the same work done, in that case the power will also be same. So power depends on the time, but the work does not depend on time. Work depends on the force and the displacement. Then we have the efficiency. Efficiency is actually when we compare the useful work compared to the total work done or total energy input, we call that as efficiency. Or it can also be useful power output divided by total power input into 100. We also call that efficiency. So efficiency is actually a comparison, like say an object is dropped from a certain height. It has a gravitational potential energy of 100 joules. And just before it hits the ground, it has a kinetic energy of 70 joules. So what will happen? Remaining 30 joules of energy is wasted because of the resistive forces. If I want to calculate the efficiency of conversion of gravitational potential energy to the kinetic energy, so what is the input energy here? The input energy is 100. What is the useful output? Because we got the kinetic, that is useful output into 100. So when we simplify, this will be 70% efficient. So what proportion of the total input energy or what proportion of the total input power is converted into the useful one or what we want, that percentage is refers to efficiency. Efficiency you can represent in percentage or you can also represent in fraction. Both ways it is acceptable. So the useful work divided by total input into 100 or a useful energy output divided by total energy input into 100, that's also efficiency. But if I want to calculate the efficiency on inclined surface, say an object is on inclined surface, we applied a force F and the object moved on this inclined surface, distance d. And while we are moving this object, it loses some of the energy because of the friction. Some of the energy is lost, okay? And the weight of an object which is acting downward, by this force F, we move the object to a height h. I want to calculate the efficiency of this process. The formula for efficiency is a useful energy output energy or power or work divided by input, the total input into 100. I want to calculate the useful. So what is the useful? For example, the work done by this force will be force into distance. And because of this, say this object was having a mass m, weight is w, mass is m. So when it reaches a height, it will have a gravitational potential energy mgh. What is the useful here? mgh or F into d? What is the useful output? mgh or F into d? The useful output. So the useful output is mgh because that is what happened, like the object is raised to a certain height or move to certain height, so useful output will be mgh. And what about the input? The input will be force into the distance into 100. So if I want to calculate the efficiency on the inclined surface, it's the gravitational potential energy divided by the total input work done multiplied by 100. Is it clear, this one? Any question or doubt till this point? So this exercise, the assignment is related to topic work, energy, and power. As we just completed the topic about how to calculate a work, how to relate the work with energy, and then how to calculate the power. MCQs, the first few MCQs, structure questions are also there in the same. Select the graph that correctly shows the variation of an object kinetic energy with velocity. You can use a chat to answer. I will explain the reason as well, but just use a chat to answer how kinetic energy and the speed are related to each other. Is it A, B, C, or D? And don't bother about answer being wrong because this is just a practice. So I want the participation from everyone. Which graph shows relation between the velocity and the kinetic energy? The formula for kinetic energy is half mv square. Don't bother about answer being wrong, as this is just a part of like you're understanding the topic. So it's not an issue that if you did any mistake. So we know kinetic energy is half mv square, 1 by 2 mv square. So mass is constant, 2 is also constant, 1 and 2, this whole is constant. So what is the relation between the kinetic energy and the speed? So kinetic energy is directly proportional to speed square. So what does it shows? The kinetic energy is directly proportional to speed square. It shows that like if a speed is double, kinetic energy will be 4 times. If speed is 3 times, kinetic energy will be 9 times. If speed is 4 times, kinetic energy will be 16 times. So which graph shows that if you double the speed, kinetic energy 4 times, and you triple the speed, kinetic energy will be 9 times. So it matches with option D. So D is the right answer for this. The next is a block of mass M is placed on a bench. A horizontal force F is applied. The block accelerate along the bench and travel a distance D. At time t, it reaches a velocity v. The work done by the force on the block is, so there's a block of mass M which is placed on the bench. A horizontal force F is applied. This horizontal force moves this object at a distance d and in time t. And the speed of the object is v here. The work done by the force on the block is, so whenever we want to calculate a work is force into distance. So which force? We take always the force and the distance which are parallel. So F into D, so A will be the right answer. In question 3, a 1.8 kg mass is suspended from the end of a spring which was having an original length of 0.04. The spring extended and now it's 3 times the original length. We attach a load which is 1. So 1.8 multiplied by 9. Why? Because when we attach, mass is not the force, weight is a force. And weight is what? Weight is mass into gravity. So the mass is 1.8 multiplied by gravity is 9.8, which is, so the total weight of this is 17.64 Newton. And 0.04, because it becomes, as I mentioned, now 3 times the original length. So 0.04 multiplied by 3. So that is equals to 0.12 meter. So how to calculate a work? Work is force into distance. So what is the force applied? Force applied is equals to 17.64 Newton. And the distance it moved. Originally it was 0.04. Now it is 0.12. So how much distance it has moved? So 0.08. So 17.64 times 0.08. The work done is 1.4 joules. But whenever springs are used, you will learn that later in the work done by the spring. Because when we use a force, we use the average force. Why we use an average force? Whenever work done on the spring or work done by the spring, we take an average force. Like the original force is 0 and the maximum force is 17.64. Because this is a spring which was not having any load, and when it is loaded, it is 17.64 Newton. That is the maximum, and the minimum force was 0. So what is the average force here, which is applied on the spring from 0 to 17.64? So that will be half of it. So, and in short, the work done by the spring, it is half of the force into distance. But in detail, I will explain this concept in the next topic, which is about materials. So this 1.4 is a work done by the force. If there was a constant force was acting, like from the beginning, the force was 17.6. But here what happened? The force started from 0 and reached 17.6. So the average force will be half of it. So the work done will be 0.71 joules. You may not able to understand clearly this concept now, because still work done by the spring or work done on the spring is our next topic. So in detail, I will explain why we took an average force, why not the force which is applied. In question 4, a wind turbine is used to generate electricity when the wind speed is 10. The power input into the wind is 3.2 kilowatt. Calculate the mass of air per second turning the turbine. So we can relate this as we have a formula like example, power is equals to energy divided by time. The wind speed is there, so which form of energy it will have? It will have kinetic energy. So power is kinetic energy over time. So power and kinetic energy is what? It is half mv square divided by time is t. If I further simplify this, so power is equals to mv square over 2 into t. In the question, we have to calculate the mass of air per second. Mass of air per second means we need m over t. So if I need m over t, the mass of the air which passes every second, so I will keep m over t one side and I'll move rest other. So 2 is divided, other side will be multiplied, so it will be 2p. And v square is multiplied, other side will be divided, over v square will be equals to m over t. So now we substitute 2. The power is 3.2 kilowatts, so you have to convert into watts. So 3.2 into 10 to the power 3 divided by the speed. The air speed was 10, but it is square, so it will be v square. So 2 into 3.2 exponent 3 divided by 10 square. What's the answer for this? How much mass is there per second? So 64. So m over t is 64 kilograms per second. So 64 kg per second. That's the mass of the air which will flow every second through this turbine or hitting this turbine or rotating a turbine. Question 5 is related to elastic strain energy, again, rubber and springs. So that we will discuss later. Question 6, in an investigation of a jump of a flea, measurements were taken from a high-speed video camera. The body of a flea can provide a maximum power of 660 watts per kilogram. A flea of a mass 0.7 milligram takes 0.85 milliseconds to take off from the rest. Show that the maximum velocity of the flea is about 1 meters per second. So this is the same question because same idea we will use. So we have power is equals to energy divided by time. As the fleas start to move, so which form of energy it will have? It will have a kinetic energy. So we can say the power is equals to kinetic energy. Or we can say P is equals to KE divided by T. We have the power, it's given 660 watt, but that is for each kilogram. Like this is 660 watt per kilogram, but the mass of the flea is only 0.7 milligram. So means how I will know what is the total power? So it's 660 watt for 1 kilogram is there, like 660 watt for 1 kg. So if I have a mass of 0.5 milligram, I have to convert into kilogram. So milligram to gram, I'll divide by 1000, and gram to kilogram, I'll also divide by 1000. So this will be 10 raised to power negative 6. Because I'll divide by 1 million to convert into kg. So 660 for 1 kilogram, so 0.7 exponent minus 6 kg will be x watt. So I will cross multiply. This will give us the power. And the time, 0.8 milliseconds. So we have the time. So using power multiplied by time, we'll get the kinetic energy. After getting the kinetic energy will be half mv square. I have the mass of the flea. I have the kinetic energy, and 2 is there. So we can take a root to work out the speed at which this flea will move, which is about 1 meters per second. Is it clear? I did not solve the question. I just explained the idea. Is it clear, this one?